as I said, this example is a little bit more challenging. Again, it's very wordy. It's a long story. So here goes. We have a water tank that has the shape of inverted circular cone. So the water tank has the shape of an inverted circular cone with base radius (2 meter) and height 4 meter. Okay, now, if water is being pumped into the tank at the rate of 2 cubic meter per minute, so let's write it. If water is being pumped into tank at a rate of 2 cubic meter per minute, find the rate at which the water level is rising when the water is 3 meter deep. Okay, so let's finish this up. Find the rate at which the water level is rising when the water is 3 meter deep. All right. Woo. Long question. So let's try to draw a sketch here, or to sketch the problem. So we have an inverted circular cone. In other words, the base of the cone is on top, like so. And we know that the dimension of the cone, let's do, this is the axis of the cone. So this much, let's call it R, and we know it's equals 2 meter. And this much is the height, and it's equal 4 meter. Okay. I'm going to position the origin of the my coordinate system at the tip of the cone, at the bottom of the cone. I think the book will place it on top, but I like to put it over there. And what happened is there is some water coming here, so let's say you have some kind of a valve here, right? And the water is pouring into the tank, like so. And the water level is rising. So let's say at the time when we discuss this, the water level is 3 meter deep. So this direction is y, so we're talking about a case where this quantity y equal 3 meter, right? And we have dv dt, and we want to know what is the y dt. So right here, the water level is rising at a rate of dy dt, and this is what we need to find. Okay. So now we can look at what's given and what we need to come up with. So what's given, first of all, the physical dimensions of the tank. R equals 2 meter and H equals 4 meter. Okay. Also, what we are told is that the water is being pumped at the rate of 2 cubic meter per minute. Well, the volume is in cubic measured in cubic meter, the time in minutes. So dV dt is 2 cubic meter per minute. Notice that whenever we are dealing with derivatives, derivative is a rate. So the unit of the derivative need to match the unit of the rate. In this case, we are talking about volume over time, and the unit of the derivative reflect this ratio. And we need to find it at when y, the water level, is 3 meter. Okay, so dv dt when y equals 3, then this quantity equals 2. And I think that's conclude the data that is given to us. What we need to find, of course, is dy dt. And again, in anticipating the answer with our present coordinate system, the solution should be positive. Okay? As the water level is rising in a positive direction of y is upward. What you don't know is the volume of a cone, unless you do know it. So before I said what you don't know, let me see if anybody does know what is the volume of a cone. All right, so you probably know what is the volume of a cylinder. Right, it's the base times the height. That always be the case when you have what we call a prism. And the cone is 1/3. So very good. The volume of the cone, the volume will be 1/3 of the cylinder, the volume of the cylinder, which is pi r. And again, the cylinder, we're talking about the volume of the cone, the tank, not the water. So I'll put in parentheses the cone here, the tank. Sorry, this is supposed to be tank. So it will be pi r squared times h. On the other hand, if I want to find out the volume of the water, I need to change something. It's still going to be 1/3 pi, but r will be the radius of this circle right here. This is r. Okay, the uppercase R is the base, the radius of the circular base, but the lowercase r will be the radius of the circle that is the base, the circle at the top of the water or the water level. So it will be r squared, and the height of the water will be y. So this is the volume, and when we take the derivative, then on the left side we'll have dv dt, which we know, and then on the right side we have the result of the implicit differentiation. But at this point, I see that I have two variables on the right side. I have both r and y, and both of them depend on the time, because as the water level is rising, then r is increasing and y is increasing. I want to find dy dt, so I'm interested in expressing as a function of y. I want to eliminate r and express it as in terms of y. Okay, so we want to express R in terms of Y. So how we go about it? Well, we go about it by setting a little similar triangle scenario. If you look on the top of the page, and we have similar triangles. How so? Well, if you look at R over H, that is the triangle that is the profile of the tank itself. So we have R here, and it's equals 2, and we have H here, that is equal 4, right? And then we look at the shaded, the water level, and then at the water level we have R, and we have Y, right? And by similar triangle, we see that R over Y, let me put it here. This will be Y, and this will be H. This will show it a little bit better. The ratio R over Y is the same as the ratio uppercase R over H, or 2 over 4, or 1/2 for that matter. And now I can express R in terms of Y will be R equals 1/2 Y. Okay. What it does, now I can express the volume of the water in terms of Y only. Going back to the volume equation, then we have the volume of the water one-third pi. Instead of R squared, I'll have Y over 2 squared, then multiplied by Y, or I'll have, this is 4 times 3, so I have pi over 12 times Y cubed. And now I'll differentiate. So differentiate, and you get dv dt on the left equals pi over 12 times 3y squared dy dt. Okay? Now, all of these are known quantities. We know dv dt equals 2. Here we can simplify it as pi over 4. Y equals 3. And dy dt is the quantity that we want to solve for. So we end up having dy dt we have 9 pi on top, and then divide by 4, so it will be 8 divided by 9 pi. And the unit will be meter per minute. And it's positive, so it does pass the common sense test. As I said, this problem is a little bit more challenging than the previous related rate example.